If you look back at the last few classes, we always dealt with the case where the reference frame was fixed. That is, regardless of whether we're using a rectangular coordinate system or a polar coordinate system, this point from which we're taking the measurement is always fixed or stationary or inertial. Okay, and that is convenient as we start learning about these methods of studying motion. But in a lot of cases, we don't have that convenience, and numerous measurements may arise from these non-fixed non-inertial reference frames. For example, you're viewing something from a moving car. So if the car is moving, it's not stationary, then the velocity that you're observing is not going to be the velocity of the object that you're observing, because you have to take into account the fact that your car is moving as well. The same applies if there's acceleration, right? And if there's circular motion, then you have to also account for the acceleration that comes from just the fact that that reference frame is rotating with respect to some axis of rotation. So, to account for the possibility of having non-inertial or non-stationary reference frames, we have to study relative motion. An example, a very simple one, would be in one dimension where you have a car that's driving east at some speed and you're traveling east at some other speed. And the question is, how fast would you appear to the other car? Right. So this is something that you've studied before. This is something that you've seen in day-to-day life. Um, it is relative motion analysis that allows us to extract useful information in such cases. So let's generalize this to the case where you have some position of some body B given by position vector B, and there's another position vector for body A given by position vector A. And now what you're doing is, from this point B, you're looking at A. So you have essentially a position vector that denotes A with respect to B. Okay, so this is A with respect to B. It's from B, you're looking at A. That's what it means. So this here is the position of A with respect to B. So simply by vector addition, you can then state that, well, maybe you should think about how these vectors are related. There's this vector, and this vector. How are they related? Position vector B plus position vector A with respect to B is equal to position vector A. I hope you got that. This plus this is equal to that, right? Um, so I like to remember it as the position vector of A with respect to B is equal to the position vector of A minus the position vector of B. The reason I like to remember it that way is because it comes in the same order. So A with respect to B, A, B. Okay. If I were to differentiate this, then I will then obtain that the velocity of A with respect to B is the velocity of A minus the velocity of B. And if I were to differentiate that again, I get the acceleration of A with respect to B is equal to the acceleration of A minus the acceleration of B. With just these relations, we can do relative motion analysis, which then allows us to account for how would velocity of something be with respect to something else, or the acceleration be with respect to something else. So based on your reference system, if it was B and B has its own acceleration or velocity, then these sets of equations can help you to account for that when you extract information about the velocity or acceleration of A. So what's worth noting here is that I've just defined them as vectors, and so these remain just vectors, whether it's in the rectangular coordinates, the polar coordinates, whatever it is. You can make use of these relations, and we'll see that in a bunch of problems. All that you're going to be applying now is this, in addition to everything that we've been studying before, which is circular motion, polar coordinates, rectangular motion, and so on and so forth. Okay, let's do a very simple one-dimensional problem, the one that I just spoke about, where car A is driving east at 60 miles an hour, while you are traveling east at 45 miles an hour. How fast would you appear to the car? This is, I think, pretty elementary. We can write down that velocity of A is 60. It's to the east. You can represent that with I hat. And your velocity, I'm just going to call it VU, is 45, also to the east. uh, how fast would you appear to the car, which is the velocity of u with respect to a, is essentially the velocity of u minus the velocity of a, which is 45 minus 60 I hat, giving you minus 15 I hat miles per hour. What does the minus sign mean? It just means that it will be 15 miles per hour to the west. Okay, so that's just an application of this here, except that now the vectors are all just aligned along the I hat direction. Let's do a more interesting problem. So I went ahead and wrote down the question. Take your time to read this. But essentially, there is this Airbus A380 that is cruising northward at 900 kilometers per hour, and you're seated in a window seat. You're looking at plane B that is oriented 60 degrees away from you. Now, to you, the plane moves perfectly eastward, which means that it's as if this plane is oriented in this way and it's just moving to the east away from you. Okay, what is plane B's velocity is the question. I hope that's more interesting. Um, I guess it makes sense for me to state that if the plane is oriented 60 degrees away from you, then this plane is actually traveling in this direction. Okay, so you can either make that as an assumption or consider that there's no drift in the plane, and so the plane, if it's oriented this way, is traveling straight in this direction. You can pause and come back. I'm going to solve it now. It's always a good idea to write down what is known and what's unknown. Essentially, the velocity of B is unknown. The velocity of A is 900. I'm going to keep everything in kilometers per hour. J hat. And it says that the plane moves perfectly eastward to a passenger in A. So the velocity of B with respect to A has no J hat component. That's what this means, right? If it is moving only to the right, then there is no component that's causing it to move upwards or along J. So this is what's stated. You can now try solving this. The velocity of B is unknown. The velocity of A is known. If you can write the velocity of B with respect to A, there's going to be velocity of B minus 900 J hat. Thing is, we don't really know what is this vector except that it is oriented in this direction, right? So if I were to name it something like V, being the magnitude, we can write then that this is V cos 60 along J hat. I'm taking the component along J hat, so that's V cos 60 plus V sine 60 I hat minus 900 j hat, where this here is now the vector b. So if I were to now collect the terms, I have v cos 60, which is v by 2, minus 900 along j hat, plus v sine 60, which is root 3 over 2, I hat. This here is your velocity of b with respect to a. And from the statement that the passenger sees that the plane is moving perfectly eastward, that means that this here is equal to 0, or v is equal to 1800 kilometers per hour. Essentially what we've done is we've defined that this here is the velocity of b, sorry, the velocity of a. This here is the velocity of b, and that the velocity of b with respect to a, which is in this direction, is purely along the eastward direction. There is nothing along the vertical direction. So those are the clues. We now made use of that to then obtain this. Is this your answer? Be careful. It asks you for plane B's velocity, not the speed. And so you should then write down that the velocity of B is this V cos 60 along j hat plus V sine 60 along I hat, or you can do the math, but 1/800 by 2 j hat plus 1/800 root 3 by 2 I hat. This here would be your final answer. Okay, because ask for velocity. Always be careful about that. The next question is that you are approaching a roundabout at a speed of 20 meters per second, and you see that there's a car that's executing circular motion in this roundabout. And because you see that, you start decelerating at 3 meters per second square. Decelerating automatically means that the acceleration is equal to minus 3 meters per second square. Okay. It's known that this roundabout, which has a radius of 150, so this here is the radius of the effective travel. So this person is executing circular motion about this radius of 150 meters at constant speed of 15 meters per second. So that is this person's speed, or information about their trajectory, and car B is approaching at 20 meters per second. Now your question is to determine the speed and acceleration of A as seen by B. Okay, so that is, what is the velocity of A with respect to B, and what is the acceleration of A with respect to B. You can pause the video and try solving this yourself. So the first thing is that because it is at constant speed, A tangential is equal to 0. I guess I should put that this is for car A. A normal for car A is unknown. The speed of A is 15 meters per second. For car B, the speed of B is 20, and the acceleration of B is minus 3. Well, that's incorrect. This would be just scalar magnitude, but let's do everything in terms of vectors. Now, velocity of A is 15 meters per second j hat. Velocity of B is 20 meters per second minus I hat. And the acceleration of B would be 3 meters per second square along I hat. Okay, so velocity in this way, acceleration is in that way. That's why it's deceleration. Okay. What can we say at this point? This is the acceleration of A tangential is 0. Normal, we can directly say that this is v square over r. So magnitude is 15 square over r being 150, which should give you 1.5 meters per second square. What direction is that going to be? What direction is the normal component of A? It's going to be towards the center, right? So it's minus I hat. So at this point, we have pretty much everything we need. If you need to obtain the velocity of A with respect to B, all you do is subtract. So you get um, 15 j hat minus 20 minus I hat, which gives you 15 j hat plus 20 I hat. But the question asks you for the speed, right? So that is the magnitude of this vector, which should give you root over 15 square plus 20 square, giving you 25 meters per second. Do the same for acceleration. Here, the acceleration of A is just 1.5 minus I hat meters per second square, because this here is 0. So the acceleration of A with respect to B is the acceleration of A minus the acceleration of B is equal to minus 1.5 I hat minus 3 I hat, giving you just minus 4.5 I hat. Okay, so I hope that was reasonably easy to do. Let's do the next one, which is, I think, quite interesting. So before the time of wind tunnels, when they were studying aerodynamic effects on race cars, what they would do is they would tie strings on the race car using tape. You might have seen this in the movie Ford versus Ferrari. And as they drive the car, they want to see that this string is not being lifted up, because if it is lifted up, then there is some upward aerodynamic force which reduces the grip and the ability of the car to turn. Instead, you want to see the strings stuck on the car. Um, so they should look like this and not like this. Okay, that's what they're looking for. Whenever they see that the string is going upward, then they have to do something to address that problem in the aerodynamic flow. Now, we're trying to develop a interesting case study where you're looking at the aerial footage of a car that is traveling in this orientation. So it's 60 degrees to the vertical. Well, probably looking from the top. So probably 60 degrees to the north. And you have that there's a known speed of 10 meters per second. Of course, you know the speed of the car. And you have those strings attached. And even though the car is moving in this direction, you have that the strings are oriented at 30 degrees away from the direction of motion of the car. Okay, it's not 30 degrees with respect to the uh, vertical or the north axis. It's 30 degrees with respect to the motion of the car. So, well, I guess this might make it look like this is vertical. So I'll redraw that. The car is oriented 60 degrees from the north axis. And this here is what the strings that are attached to the car look like. They are oriented 30 degrees away from the axis of the car. Now, it shows that the strings are angled 30 degrees and the car is traveling at 10 meters per second, 60 degrees east from the north. All you know about the wind speed is that it is acting southward. You don't know the wind speed. Okay, and for you to do your calculations and make a recommendation for the race car team, the question asks you what is the wind speed. So go ahead and try to attempt this problem. always a good idea to create a sketch of the vectors that are involved. Okay, I hope that you pause the video and you try to solve it yourself. This is now me solving the problem. So you have that this here is the velocity of the wind. There's the velocity of the wind, you know it's downward. The windsock, which I'm sure you've seen, is something that rotates based on the direction of the wind so that you know in what direction the wind is flowing. So this here is the wind velocity, the vector. It's also given to you that the car's velocity vector is in this orientation. This is 10 meters per second, and I'm going to call this the velocity of the car. And these strings over here, they represent how the wind would be with respect to the car. The velocity vector of the wind with respect to the car is in the orientation of 30 degrees. So this here is the velocity of wind with respect to car. And if I were to now mark the information about the angles, essentially this here is 30 degrees. Well, actually, to be more precise, this here is 30 degrees, right? It's between the direction of the car motion and the string here, which is 30 degrees. But the fact is that the car is at an angle of 60 degrees with respect to the north. So this here is 60 degrees, which essentially means that this here is also 60 degrees, which is how you get that this here is 30 degrees. Okay, so this was a bunch of vectors and their relation between them and the angles and so on. So let's say that the thing that's unknown is the velocity of the wind. So let's say the velocity of the wind is some v in the minus j hat direction to represent the southward direction. And the velocity of the car is 10 cos 60 j hat plus 10 sine 60 I hat, which is a component of this along j hat and a component along I hat. So we don't have the magnitude of this vector either. So let's say then that the velocity of the wind with respect to the car is some x, and it is cos of, I would say cos 30 in the minus j hat direction plus x sine 30 in the minus I hat direction. So that is a component of this along this and along that. Okay, so at this point we have two unknowns, v and x. What are we looking for? We're looking for just this, but we may have to deal with this as well. So if we were to now write the relations, we have that the velocity of wind with respect to car is x cos 30, which is x root 3 by 2 minus j hat, so this much, minus x sine 30, that's x by 2 I hat. So I just wrote this down, is equal to the velocity of the wind minus the velocity of the car. So that is v minus j hat minus 10 cos 60, which is 10 by 2 j hat minus 10 sine 60, that's 10 root 3 by 2 I hat. So this now is your new, well, it's just from the relative motion analysis, but if you were to now relate the j hat components together, that's by doing a dot product with j hat, you will get one relation as minus x root 3 over 2 is equal to, you will get minus v minus 10 by 2 or minus 5. That's one relation. And the other relation from I hat, you will obtain minus x by 2 is equal to minus 10 root 3 by 2 or minus 5 root 3. Okay, so essentially this is giving you x as 10 root 3. And if you were to now apply that above, you will then get that 10 root 3 times root 3 by 2, that is 30 by 2 is equal to minus v minus 5. There's a minus there as well. And with that, you get v is equal to 10 meters per second. Okay. I hope that that was interesting, wherein you saw how you can actually make use of relative motion analysis to then obtain some information of an unknown quantity, that is velocity of the wind. We have now found to be 10 meters per second downward, simply by analyzing the data that's provided to you at this instance. Okay. I think we're well equipped to do another problem now, which is this one here. Again, I hope that you're pausing the video and trying to solve it yourself. You essentially have a raindrop with a terminal velocity given to you. Some car is driving at some speed and has a windshield angled at 50 degrees from the vertical. So from the vertical, it's angled at 50 degrees. Now I drew it in this way because it doesn't really tell you if the car is going to the left or the right. So I'm assuming that the car is going rightward, and this is how the windshield is oriented. Of course, you could have done it the other way, where the car is going leftward, and this here is the windshield of the car. That's also fine because it doesn't affect anything related to the answer. So terminal velocity is 10 meters per second. There's a windshield that's angled at 50 degrees. At what angle theta will the raindrop strike the windshield? Okay, so it's not as straightforward as it would just be 50 degrees, of course. It asks you to measure the angle theta from the normal to the windshield. So it's telling you how to make that measurement. Go ahead and try to solve this now. Okay, so I am keeping the windshield orientation this way, 50 degrees with respect to the vertical. You have the velocity of the raindrop as 10 meters per second downwards. That would be minus 10 j hat. And it's given that the velocity of the car is 100 kilometers per hour. So that would be 100 times 5 by 18 meters per second. I'm taking it as going rightward. So I hat meters per second. Why do I have to make the conversion? Because the velocity of the raindrop was given in meters per second, so I need to keep everything consistent. So these are vectors, and now I have to write the velocity of A with respect to B is minus 10 j hat minus 27.8 I hat. So that is the velocity that the raindrop will make with respect to the car as the car is being driven. Now the question asks, at what angle will the raindrop strike the windshield? Essentially, this here is the velocity of A, and this here is the velocity of the car, which we are calling B. I have the magnitudes as 27.8 and 10. And the velocity of A with respect to B, which would be this vector here, is the velocity of A with respect to B. What angle would it be making with respect to the windshield, with respect to the normal of the windshield? So, okay, if I could find this here, what is this angle? This theta is such that tan theta is equal to essentially this 10 and this 27.8. So 10 over 27.8 giving me 20 degrees. Sorry, giving me theta is equal to 20 degrees. So now if I were to sketch that same uh, sketch that I initially had for the windshield, I can then have that with respect to the horizontal, there is an angle of 20 degrees. And the question asks for your answer to be with respect to the normal, to the windshield. So if this here is your windshield, I guess I'm going to say that this is 20 degrees, just so I can sketch it more easily. And this here is perpendicular to the windshield. I guess this is why drawing good sketches is important. But if this is 90 degrees and this 50 degrees, this here becomes 40 degrees. And now this here is 90 degrees with this being 40 degrees, the normal, this being 20 degrees. So now this here has to be 90 minus 60, that is 30 degrees, which is the answer. So it was just a matter of making use of this to then stay with the guideline for the question, which was measuring that angle from the normal to the windshield. So answer 30 degrees with respect to the normal. Okay. Um, you can take a moment to go through that again. All we did was use vector properties. Here's another interesting problem where there's a car with a forward speed of 18 kilometers per hour, accelerating at 3 meters per second squared. I think I should also draw the car here before you can solve this. This here is the car. It's accelerating at 3 meters per second square, and it has a current speed of 18 kilometers per hour. The question asks to determine the velocity and acceleration of car A with respect to a person in the Ferris wheel. So the Ferris wheel, there's a person in the cabin at position B, which is 45 degrees from the horizontal. And the radius of this Ferris wheel is 9 meters. Okay. I hope that's interesting. You have now that there's a Ferris wheel rotating, so there's circular motion being executed here. There's omega of 3 rotations per minute. You can assume that it is a constant speed. And you have the car that's accelerating rightwards with a certain speed. Go ahead, stop the video and try to solve it yourself. Okay, so I'm going to write down the velocity of the car first. So VB is equal to 18 kilometers per hour, which if I convert it to meters per second, it would be, sorry, this is VA, the velocity of the car, is this much meters per second rightward, is 5 I hat meters per second. And the velocity of the cabin is going to be tangential, so it's going to be in this direction. And the magnitude is going to be R omega, right? This is omega, R omega. So it looks like it's easier for me to write the speed first. So the speed of this person here is going to be R omega, which I can write as 9 times omega being 3 times RPM to radians per second. So 3 times 2 pi radians in 60 seconds, giving me, I think it is 2.83 meters per second. I will now write it down as a vector. So it's 2.83 and the direction is in this way. Maybe a good idea to draw this as a vector itself. So it's 90 degrees with respect to this here, which is at 45 degrees away, which then allows me to write here 45 and here as well 45 degrees. So this is 2.83 in magnitude. If I were to write it as a vector, it would be 2.83 cos 45, that's root 2 I hat minus 2.83 cos 45, that's 1 by root 2 j hat meters per second. And simply the velocity of A with respect to B would be the velocity of A minus the velocity of B. So that's 5 I hat minus 2.83 by root 2 I hat minus of minus, so plus 2.83 by root 2 j hat, which gives me um, 3 I hat plus 2 j hat meters per second as my answer for the velocity. If it asks for speed, you would have to do square root of 3 square plus 2 square. Okay, go ahead and if you haven't tried it yourself, try doing the same for acceleration. Okay, I'm going to do it now. So acceleration of A is 3 I hat. Acceleration of B is just v squared by r because there is no tangential component. So it is 2.83 squared divided by 9. In what direction? It will be towards the center. So minus 1 by root 2 I hat minus 1 by root 2 j hat. Is essentially cos 45 in this direction and cos 45 in this direction. Well, one of it was sine, one of it was cos. They both are the same value. So this here is the acceleration of A and this here is the acceleration of B. And the question asks for the acceleration of A with respect to B, which now gives me, if I were to do acceleration of A minus acceleration of B and then clean everything up, I should get 3.63 I hat plus 0.63 j hat meters per second square. Always remember to write the units. Okay. I hope that makes sense.